So this next chapter, we're going to start to think about instead of those biotic elements, now to think about the abiotic, so that non-living stuff that we've been considering in our systems. And I want to start by thinking about the Mediterranean climate in particular, which, to go back to what I discussed earlier in the first section, is important to consider in the sense that our California climate is very much governed by our proximity to the Pacific Ocean and also where we are in terms of latitude. So Mediterranean climates are considered to be systems that have cool, wet winters like California, mostly on the coast, and then also warm, drier summers. And we have that 6 month period of drought essentially every summer in many parts of California. And Mediterranean climates are particularly unique to only a few places in the world. The Mediterranean basin, as you can probably imagine, parts of northern Chile, Australia, California, and then also South Africa. And even while we have these really dry periods, there are also places in California, particularly along the coast, where we do have maritime influence of fog. The fog is usually very minor in what its impact can be. But even still, this kind of vegetable mister pattern that we see from coastal fog, all really hard to measure. It's something we call occult precipitation. It can actually help to quench the thirst of some of the perennials that have to survive through those long dry periods. Interestingly enough, another pattern that we see in the Eastern Sierras are actually what excludes places like the Eastern Sierras, the Modoc Plateau, and parts of Southern California from our California Palearctic province, and that is monsoonal influence, so summertime rains that come up from the Gulf of California and the Gulf of Mexico. So that's why we exclude these sections from the Palearctic province, in addition to the fact that they're on essentially the wrong side of those mountainous divides, but also because they don't really fit that concept of Mediterranean climate. So one of the reasons that we find so many annual plants growing natively in California and also many plants that will die back during the summer months, evolutionary biologists believe, is because we see such an incredible dry period that exists every year. And that essentially, if you're an annual plant, there is a lot of sense in being adapted so that you will die back during the summer and only have to grow and reproduce during the wet time of year, during the favorable times of year. And thinking about annualness, that also can then, because of we have this expedited rate of growth and death and generation time, folks have also considered that may be something that influences speciation and the neo-endemics that we see emerging in California, particularly in those drier habitats like Southern California. We also have to consider that California is spread out across many latitudes, so from 32 to 42 degrees north. As you may already be aware, the sun's rays are not consistent across all of the latitudes. So if you're down at the equator, you're getting more direct sunlight throughout the year. But as you go further to the north and further to the south, those rays are more oblique. And the way I would kind of analogize this is if you imagine standing up and the sun's rays are striking you at noon on the top of your face isn't as hot as if you were to lay down and then let those rays strike your face directly, right? So you'll feel that difference just on your face depending on how you orient it to the noonday sun. That's essentially what's happening with planet Earth. And then again, to think about that gradient across those latitudes, we can think about how also if we go from the coast towards the inland areas, we have fog on the coast. And that fog is produced by cold upwellings in the Pacific Ocean. Those upwellings, when they meet the warm air mass that's along the California coast, combine to produce that fog that we see along the coastline. And then throughout all of California, again, that Mediterranean climate, which is informed again by atmospheric pressure regimes. And we have this thing called the North Pacific High, which parks itself off of our coastline during the summer months and essentially redirects storm fronts north or south of the Palearctic province, meaning that we don't have really intense rain or other weather regimes coming ashore. So since we're talking about air masses, I want us to think about these things called convection cells that are commonly discussed in meteorology. I'm just going to kind of generally overview these because they're not so crucial to your understanding of ecology, but I think they'll help in making sense of more global patterns. So convection cells are essentially a conveyor belt of air that rises as it warms and then settles as it cools. And what we see is that at the equator, we have warm air that's rising. And as that warm air rises, it carries with it, because it has greater capacity to carry, moisture. As that air rises, it starts to cool. And as the air cools, its capacity to hold moisture drops, which means that we have precipitation, rain, snow, what have you, that comes out of that air mass and is deposited into the oceans and onto the land. By the time that air mass has completely cooled and starts to settle at 30 degrees north or south of the equator, it's now very dry. And that means it's going to soak up more moisture from the atmosphere, from the land mass, but also there's going to be no precipitation or less precipitation to come out of that settling air. And so as a result, if you look at a map, you'll find that 30 degrees north, 30 degrees south are typically where we find desert regions. From those 30-degree latitudes, as we travel north and south, we then start to pick up more heat, and we also pick up more moisture until we reach about 60 degrees north and 60 degrees south, where again we see another convection cell, and that convection cell repeats the same pattern we saw, where the warm air that rises loses moisture, and we have precipitation before cycling back towards either zero or cycling back up to towards the polar regions. And so what we see then at those more northerly latitudes of 60 degrees north and south is more rain. And so you can imagine then that at the equator and at 60 degrees north and south, you have rainforests, either equatorial rainforests or temperate rainforests. And of course, it's important to realize that this is not just an influence of these patterns of moving air, but also we have oceans. And on the Pacific, we have an ocean that takes up an incredible amount of area, and therefore will have an incredible influence on the conditions that we see climatically on our land masses. The first influence we have to consider is that water has a different heat capacity than air. So that means during the summer months, it will absorb a lot of heat as an insulator. And then during those winter periods, some of that heat will be given off. So we have essentially thermal regulation that keeps our coastal climates pretty even throughout the year because of this insulated capacity that exists in our oceans. But then also there's something else, that's the El Nino event that happens every decade or couple of decades, which is where we see oscillations in some of these currents, both atmospheric and then also oceanic current in the southern part of the Pacific off the coast of South America. And what that will drive then, and this specific information isn't very relevant to this course, but what that will drive is variation in weather patterns experienced in our floristic province and really throughout the Pacific Basin. So in California, when we have an El Nino year, where we have this change in patterning of the movement of these oceanic currents and then storm fronts, we see that Southern California tends to be wetter and receives a lot of precipitation. Northern California tends to be a bit drier, and that's true also for Oregon and Washington. And then the Bay Area tends to be kind of a toss-up between the two. We also have events that are the reverse of El Nino called La Nina. And in that case, we see wetter Northern California seasons, drier in the Southern California regions. But what we're seeing is really two things. Again, that latitudinal gradient affects incoming solar radiation across the floristic province. It will affect kind of what we're experiencing in terms of those convection cells, but also it will influence, even within a given year, what a species may be experiencing in terms of climate. So you can imagine that if there is some species whose range is spread out across that floristic province, maybe through the Central Valley of California, it may be that the northern populations are experiencing lots of rain, the southern populations are not. And this is another element that can then lead to local adaptation and could also end up driving speciation if those patterns and inconsistencies persist. And speaking of inconsistencies in weather, I think often we think that today, as we encounter climate change, we're seeing a lot of variation in what the weather patterns look like. Things are more turbulent. The rain may occur later in the year, sometimes not at all, or may come earlier. We may have colder winters or warmer winters. Obviously, this is something that is of concern, but also it's worth noting that because there's a lot of history in terms of how El Nino and also how we see these cells convecting air and weather patterns across California, there is sort of a history in this landscape for a lot of variability from year to year. An example of that then plays out in what plants we'll see each year growing. So when I first started working at Golden Gate National Recreation Area, it was right after a really, really wet year on the wings of multiple years of drought. And the whole hill slopes were covered in all of these beautiful indigo colored lupin. And I thought it was going to look like that every year. But as it turned out, the next year it was very dry, and actually there were no lupin at all. And this speaks to this concept that we refer to as storage effect. And it's very common among annual plants in particular, but can also be seen in perennials and species that tend to enter dormancy and die back. And essentially what the storage effect is showing us is, just as before we talked about partitioning of resources in a spatial sense with that idea of realized niche. Now we're talking about partitioning of resources across time. So essentially, different species are engaged in a timeshare agreement, though not in the scammy sort of way, that leads to each of them having their moment in the sun, depending on when the particular yearly conditions match up best for them to be able to grow and germinate and reproduce. So a really wet winter could lead to lots of lupin, but maybe a drier winter might lead to more Festuca rubra, which is a type of grass, or maybe more Sedelcia, or some other wildflower coming forth. So the storage effect allows for different species to essentially be able to share this space, but spread out across time. And the way they do that is with robust seed banks. In other words, seeds that are produced that can remain dormant for decades, sometimes even 50 years at a time. And an example that is in a non-climatological vantage would be with fire ecology, where we often talk about fire followers, which are species that grow and may have emerged only after fire in habitats after burns. So in thinking about these concepts of niche partitioning and thinking about that rotation of what species are present, I want to go back to what we discussed earlier in our second chapter about succession, to again think about that rotation of what species are present and what will lead those species ultimately to appear on the landscape or to cede territory to other species. And to start out with, I want to kind of summarize this concept that was put together by Connell and Slater in 1977. I've included a link if you'd like to read this in more detail. But effectively, many of the changes that we see that can lead to or initiate succession are driven by disturbance. When we think about those disturbances, the first thing we need to do is think about whether or not they are high intensity or low intensity. So you can imagine that if a disturbance was highly intense, let's say a landslide, or maybe the retreat of a glacier, or some area that was able to be scraped bare, so there was only abiotic elements that were present, then we might see that the first species to come in are going to be those that can make best use of those limited resources. This will include early colonizers that we sometimes call pioneer species. But if that disturbance is low intensity, and that could include even just climate variability, then we might think that any species could be able to fill into that space. But there's going to be limitations in terms of what can actually access that space. So an example that I would give then is thinking back to our conversation on fire followers and storage effect. You can imagine that, if we have this high intensity fire that burned through this forest, this would be, in a sense, low intensity effect in the sense that there's still soil. There's still a space where if you were to put a pine cone and a pine seed, it would probably be able to grow just fine in this habitat following this disturbance. The problem, though, is we may have destroyed the seed bank. We may not have any pine trees that still have seeds that are in close enough proximity to disperse into this habitat. So even while this might be a space where a pine tree could grow, it's likely that we won't see it growing unless it can disperse into this habitat. And so what we would see instead would then be species that have dispersal mechanisms, maybe dispersal through wind or through some organism that could carry them into that place, growing first, or species that have potentially more robust capacity to exist within a seed bank and then recolonize that space. Going back to our consideration of these disturbances, we also want to think then about when a species and the community of species that establish themselves first, when they take over that space, how will that landscape change as they grow in that space? So we could have species that are some of those pioneer species, those earlier successional species, maybe more ephemeral species, that may act to prevent other species that don't conform to that community type from filling into that space. And ultimately, what would disrupt that would be something like another disturbance factor. So an example of that could be after fire, we might see lots of manzanita or other shrub growing in at high density and preventing pine trees from filling into that space. We can also think of examples where a species may modify that space in such a way that other species are able to move in and grow in that space. And that comes in two flavors. It could be in the case of the alders that I identified in the second chapter, where the alders create a habitat that's nurturing for conifer species to grow and to fill in, and ultimately those alders then die out. Or we could see a situation where an organism creates space for other more woodier plants to fill in, but ultimately both those earlier successional species and later successional species that exist in that space. So both our ephemeral species and our woodier species can coexist in that space, and neither is losing territory, so to speak. In the end, though, when we have that recruitment of all these species, what will reset those systems will again be other disturbance patterns like wind or landslides or disease or fire. And that's what I'd like to kind of round this out with, is talking about fire and fire ecology. Fire is a fundamental aspect of our landscape because, again, with Mediterranean systems, we have that long period of drought throughout the summer, which means greater chance for things to dry out and to be prone to burn. I think that with fire in particular, this is an interesting conversation piece because there is a natural element in the sense that fires in the interior of the state have been historically lit in many cases by lightning. But we also see that on the coast, there can be a lot of historical fires recorded in soil or in plant tissue that we can look at. And we know that some of those fires in both habitats were ignited not just by natural elements, but also by humans who have lived here. And so there's a long history of fire management, both for cultural ends and also for ecological purposes. Pictures shown here highlight efforts to restore some of those practices, traditional ecological knowledge practices utilized by the Kuruk tribe up in the Klamath River watershed in Northern California. And they've been doing a lot of work with the Forest Service there in the Klamath Trinity to bring back to those Aboriginal lands practices that help to revitalize those spaces by either thinning and clearing out understory brush and helping to promote some of those species that respond best to fire. It's also worth noting, though, that some of those fire practices also have benefit for cultural ends, such as opening up space, historically more so for maybe hunting practices, but also in basketry and for a lot of wiat and toloa basketry, burning of plants back to the ground that can then lead to new growth that may have straighter grain or be more prone to be free of parasitism are really important in creating those materials that will be used for basketry. And then below that picture of that structure, that's the woodward fire that burned in Point Reyes Station, and that's Kuliloklo, which is a archaeology site that's been reconstructed and is co-managed by the park, and Great Rancheria, which is includes the Miwok peoples. So to think about fire and its effect on plant life in particular, a few adaptations that we see in California and in fire-prone areas are seeds, again, that germinate easily after fire when there's more light available. We can also see things that grow back from burls, such as this manzanita at the far right, which after burned to the ground can produce vegetative material from woody structures. We also see something known as serotiny in some of our pine species like ponderosa pine, whereby heat allows that pine cone to open up and release seeds. And through that fire, it cleanses the ground of sometimes pathogens. That means that this seed will have a better shot at actually germinating and breaking ground. Previously, I talked about density, and I'd like to return for this last section to the concept of density to think about the ways in which density of forest stands can affect the spread of fire. And this is a pretty multifaceted topic, but I've constructed a couple of videos, and with a very simple model of having a pegboard where I have for every centimeter one match, we're going to look at how fire moves across this pegboard, across this matchstick forest. So here's our first video. Again, that's a distribution of one match per centimeter. I'm lighting up one of these trees on the edge of our forest. And what I've also done is I have a fan on the left side of the screen that's directing just a slight airflow so that we'll have the fire moving in a consistent direction. And I turned the audio off on this video because I was doing this in my kitchen. And at this point, I was starting to get a little worried, and I think I shot an expletive. So I turned the video off. But notice how the fire is moving in a uniform direction. Notice how all the structures of the matches are bending in a consistent direction. So when you go out on the landscape and you're looking at a place that's burned, look at the direction in which the tissue has moved. That can often speak to the way in which fire moved across the landscape. Also, when looking at trees, you can often notice direction that fire moved simply from where on the tree, if it's level ground, you're seeing that burn scar. Oftentimes when we look at things that have slope to them, we might see more burn scar on the upslope just because more tissues and duff and other detritus can collect on those uphill slopes. So that went pretty fast, not a forest I think I'd like to live in. And again, you can see kind of what that looked like, that pattern of burn. So I'm going to show another image. This time I've thinned my forest by 50%. So now I have 0.5 matches per centimeter. And let's see how well this one burns. So same idea, lighting one match up and consistent airflow. Something I'd like to also note, though, as we watch this video is that different forests will have different qualities of fuel. So you can imagine that a forest that's very dry, like these matchsticks, maybe having lots of fuel in that forest will lead to that fire spreading very easily. But we could imagine that a forest, such as a forest in Northern California, where it's very wet, or a place like Olympic Peninsula, a lot of moisture is held in that woody debris. And it means that that tissue may be less likely to catch fire. So you can imagine trying to put a wet log on a fire, it's not going to burn very easily. So forest stand density, even while I think for more Sierran systems and systems that are drier, reducing fuel load can be really important. It's also worth considering that systems that have a lot of woody green material can be less prone to burn. So in thinking about how to thin a system or to manage a system for fire, it's always good to really have a strong sense of the local ecology of where you're working. And you can always consult with folks like CAL FIRE or your local cooperative extension officer to get feedback on what's best for your system. So I was never able to get this fire to start, and it just speaks to the fact that we don't have that density that could lead to fire movement on our landscape. So I've done 2 more demos. This next demo is hill slope now at 45 degrees. We're back to that high density forest. And let's see what's going to happen when we light this up. And so this just sort of speaks to a kind of a central tenet, which is that when you light a match or a lighter, that flame is pointing in an upward direction. And so fire on a hill slope, even as dense as this, is going to have a intention in where it's going to want to move. And what you can see already is that that fire, it's moving upslope. We're not really seeing it move downslope. And so in fire management, thinking about the ways in which fire would move across a landscape, the contours of that space, also how oxygen may be sucked into a valley or move through a drainage drawn by turnover that we experience in the same way that we talked about convection with those convection cells of warm air rising, cool air settling. We can see the effects that landscape contour will have then on how fire moves. And you'll note I only lit half of this. But again, you can see that those lower matches, they're not catching. This fire moves just upslope. So for now, at least, those trees at the bottom of our slope are safe. So now I'm going to do a fire break, and it's the same scenario as before, except now I've got a couple matches at the very top and some matches that have still not been lit at the bottom, but all that area in between that got burned. And we're going to see what happens when we light it up at the base, and we're going to see if having a break in our fuel load can effectively protect those matches at the top of our hill slope. And again, part of the reason that I'm showing this is because CAL FIRE, if you live in a rural place, has certain stipulations about the types of fuel breaks that you need to maintain, and has criteria for how to best mitigate fire risk for your home. So I want to demonstrate kind of those ideas so you can get a sense of what that would look like in this small model. And again, there are some imperfections, so we can imagine that in an actual forest, such as a drier forest, like in the Sierras, we would have maybe a lot of dry duff on the ground. So we might have fire that's also conveyed along those surfaces, what we call surface fuels. So all those matches are going up in flames, but so far those matches at the top of our hill have not burned. So looks like our fuel break ended up working after all. So again, I just want to highlight that different systems will have different adaptations. We can look at this forest in Del Norte County on the left a 500-year burn cycle. Those trees have lots of low branches, what we call ladder fuels, but they also retain a lot of moisture. There's more living branches lower in the canopy. And also because of that density, there's less airflow. So we might expect that this is a system that may not dry out as easily, may be less prone inherently to fire. But in comparison, something on a 15-year burn cycle, like this ponderosa pine forest, less of those lower fuels, less surface fuel. It's also a lot drier. If we had that kind of density that we see in our Delmont forest, in our Plumas County forest, we might expect that that would be a system that would be very prone to going up in flames. So different forests will have different proclivities in this regard, but it's always worth, again, then consulting with local experts such as CAL FIRE on what are the best management practices for your area. And I've included some resources to those CAL FIRE links here in case you're interested in following up with that. All right, question time.